Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual firmament of the ancient world, few stars burn with the incandescence of Archimedes of Syracuse. His work represents a monumental synthesis of rigorous deduction and startling intuition, a bridge spanning the axiomatic world of Euclidean geometry and the nascent concepts that would one day blossom into the infinitesimal calculus. Among his extensive and varied corpus, the treatise on the sphere and cylinder stands as his crowning achievement, a work he held in such high personal esteem that he requested its central theorem be engraved upon his tombstone. This essay will explore the profound contribution of this text, situating it within its historical context, dissecting its revolutionary methodology and tracing its enduring legacy through the annals of mathematical thought. On the sphere and cylinder is a demonstration of pure reason conquering problems of curvature that had perpetually eluded the grasp of earlier Greek geometers, establishing Archimedes as a mind operating on a plane far above his contemporaries. The intellectual landscape into which Archimedes emerged was dominated by the foundational work of his predecessors, chiefly Euclid of Alexandria and Eudoxus of Cnidus. Euclid's Elements had established the gold standard for mathematical proof, a grand edifice of logical certainty built upon a small set of axioms and postulates. Its power, however, was most elegantly expressed in the domain of rectilinear figures, polygons, prisms, and pyramids. The world of curves and curved surfaces presented a formidable challenge. While the circle and its properties were well understood, three-dimensional objects defined by curvature, like the sphere, remained largely terra incognita. The tools of straightedge and compass, the very instruments of Euclidean construction, were inadequate for calculating the area or volume of a sphere with deductive certainty. The critical breakthrough came from Eudoxus, whose method of exhaustion provided the first rigorous technique for approaching such problems. This method involved inscribing and circumscribing a curved figure with a sequence of polygons or polyhedra. By progressively increasing the number of sides of these approximating figures, their areas or volumes could be shown to converge upon the area or volume of the curved figure itself. The method of exhaustion was a powerful tool of verification. It allowed a mathematician, who already suspected a certain relationship to be true, to prove it with unassailable logic. Its significant limitation was its silence on the matter of discovery. It offered no clear path to formulating the initial hypothesis. It was a mechanism of proof, an instrument of discovery. The central unsolved problems, therefore, remained what precisely is the volume of a sphere, what is its surface on the sphere and cylinder. Addressed in 2 books to Archimedes' friend Dositheus of Pelusium, answers these questions with definitive and breathtaking elegance. The work is a model of logical progression, beginning with a set of carefully articulated axioms and postulates. These include foundational assumptions, such as the principle that a straight line represents the shortest path between 2 points, and a more subtle postulate concerning convex surfaces if 2 such surfaces share the same boundary. The one that encloses the other possesses the greater area. These postulates, seemingly intuitive, form the bedrock upon which Archimedes builds his intricate proofs, allowing for the rigorous comparison of curved surfaces with rectilinear constructions. The climax of the first book arrives with propositions 33 and 34, which contain the work's most celebrated results. In proposition 33, Archimedes demonstrates that the surface area of any sphere is equal to 4 times the area of its greatest circle. Expressed in modern notation, this is the familiar formula where the surface area is 4 times pi times the radius squared. His proof is a masterclass in the application of the Eudoxian method of exhaustion. He considers a sphere and approximates its surface by creating a solid of revolution. This solid is formed by rotating a regular polygon, inscribed with a rate circle of the sphere, about the dia. The surface of this solid is a collection of frustums, or truncated cones. Archimedes meticulously derives the formula for the surface area of this assembly of frustums. He then employs a proof by contradiction, or reductio ad absurdum. He assumes the surface area of the sphere is either greater or less than 4 times the area of its great circle. By continually increasing the number of sides, the inscribed and circumscribed polygon laws that our assumption lead to logical impossible, thereby compelling the conclusion that the 2 quantities must. Following this triumph, Proposition 34 reveals an even more profound relationship. Archimedes proves that the volume of a sphere is precisely 2/3 the volume of its circumscribing cylinder, meaning a cylinder that perfectly encloses it, touching it at the equator and at both poles. The volume of the cylinder is easily calculated. Its base is the red circle of the sphere, with area pi times the radius squared, and its height is the diameter of the sphere, or 2 times its radius. The cylinder's volume is therefore 2 times pi times the radius cubed. 2/3 of this value yields the now famous formula for the volume of a sphere: 4/3 pi times the radius cubed. This simple, elegant 2-to-3 ratio between the volume of the sphere and the volume of its circumscribing cylinder was, for Archimedes, a discovery of cosmic importance. It revealed a hidden, harmonious order in the universe, a perfect geometric sympathy between 2 fundamental shapes. He later showed that the surface area of the sphere, 4 times pi times the radius squared, is also exactly 2/3 of the total surface area of the circumscribing cylinder. This beautiful symmetry, linking both volume and area in the same constant proportion, was the discovery he wished to be immortalized, the diagram that Cicero would later search for and find upon his neglected for centuries. A deep mystery shrouded these spectacular results. The method of exhaustion, as presented in the text, is a flawless engine of verification, yet it offers precious few clues as to how Archimedes first arrived at the 2/3 conjecture. The proofs are so complex and non-intuitive that it seems almost impossible he could have guessed the answer and then constructed the proof. How did he know where to begin? The answer to this question lay hidden for nearly 2 millennia, finally coming to light in 1906 with the discovery of the Archimedes Palimpsest, a Byzantine prayer book written on parchment that had been recycled from older scientific texts. Beneath a liturgical script, scholars uncovered a lost treatise, The Method of Mechanical Theorems, a letter from Archimedes to the scholar Eratosthenes of Cyrene. In The Method, Archimedes reveals his secret. He describes a brilliant heuristic technique based on principles of mechanics, a field he himself had placed on a firm mathematical footing in works like On the Equilibrium of Planes. He imagined the sphere, along with a cone and a cylinder, being sliced into a vast number of infinitesimally thin, parallel discs. He then conceived of these slices as objects possessing weight, which he placed on a theoretical lever. By balancing the circular slice from the sphere and the circular slice from the cone on one side of a fulcrum against the corresponding circular slice from the cylinder on the other, he could use the law of the lever to determine their relationship. This process of conceptual weighing, repeated for all the slices composing the solids, revealed that the volume of the cylinder was in equilibrium with the combined volumes of the sphere and a specific cone. From this mechanical balancing act, the 2/3 relationship for the volume emerged directly. Archimedes, however, was keenly aware of the logical deficiencies of this approach. The use of indivisible slices, or infinitesimals, lacked the rigorous foundation demanded by Greek mathematics. He explicitly stated in The Method that this approach served as a powerful tool for discovery but fell short of a formal demonstration. Having found his answer through mechanical intuition, he then turned to the unimpeachable logic of Eudoxus' method to construct the formal proofs presented in On the Sphere and Cylinder. This revelation showcases a profoundly modern scientific intellect, one that fluidly combines physical intuition and heuristic modelling for discovery with subsequent axiomatic rigour for verification. The influence of On the Sphere and Cylinder was both immediate and enduring, though its journey through history was complex. Within the Greek-speaking world, Archimedes' results became canonical, studied and preserved by later commentators like Pappus of Alexandria and Eutychius of Ascalon, whose work was instrumental in transmitting Archimedean thought to subsequent generations. The rise of the Roman Empire, however, precipitated a change in intellectual priorities. The Romans, a civilization of unparalleled engineers and administrators, valued practical application over abstract theory. While they utilized Archimedes' formulas for practical purposes, the deep intellectual wellspring of Greek theoretical mathematics began to run dry. The spirit of inquiry that produced such proofs largely receded in the Latin West for a millennium. The preservation of Archimedes' legacy fell to the scholars of the Byzantine Empire and the Islamic Golden Age. Mathematicians in vibrant centers of learning like Baghdad, including the Banu Musa brothers and Thabit ibn Qurra, avidly translated, studied, and expanded upon his work. They absorbed his methods for calculating volumes of solids of revolution, pushing the boundaries of what could be achieved with geometric techniques. It was through this twin conduit of Byzantine Greek and scholarly Arabic that the works of Archimedes were reintroduced to Europe during the Renaissance. For thinkers like Galileo Galilei, who venerated him as superhuman, Archimedes represented the pinnacle of scientific reasoning. The very problems that Archimedes tackled, the calculation of areas under curves, the volumes of complex solids, the determination of tangents, were precisely the challenges that animated the intellectual ferment of the 17th century and directly motivated the invention of calculus. The line of descent from Archimedes to the architects of calculus is remarkably direct. Bonaventure Cavalieris' method of indivisibles, which treated areas as being composed of an infinite number of lines and volumes as composed of an infinite number of planes, is a clear formalization of the heuristic reasoning Archimedes secretly employed in the method. More profoundly, Isaac Newton and Gottfried Wilhelm Leibniz, both deeply steeped in the classical tradition of Greek geometry, built their new calculus to solve Archimedean problems. The integral, at its core, is a powerful generalization of the method of exhaustion, creating an algebraic machinery that could achieve in a few lines of calculation what had taken Archimedes pages of intricate geometric argument. The fundamental theorem of calculus provided the conceptual link between finding the slope of a curve and the area beneath it, a link that Archimedes had approached but had lacked the algebraic language to fully articulate. In a very real sense, calculus provided the powerful, generalized toolkit that finally rendered the Herculean, bespoke labours of Archimedes unnecessary for future generations. In conclusion, the sphere and cylinder is far more than a mere collection of geometric results. It is a monument to the power of human reason, a work that pushed the boundaries of ancient mathematics to their absolute limit. It showcases the dual genius of Archimedes, the intuitive physicist who could weigh imaginary slices on a conceptual lever, and the peerless logician who could construct proofs of ironclad certainty. In solving the riddle of the sphere and uncovering its sublime relationship with the cylinder, Archimedes not only answered one of the great questions of his age but also laid the conceptual groundwork for a mathematical revolution that would occur nearly 2,000 years later. The simple diagram he wished for his tombstone, a sphere inscribed within a cylinder, serves as a timeless and eloquent epitaph, a symbol of a mind that found perfect, harmonious order in the abstract world of form, and in doing so, forever changed the course of science.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.